Hey folks, this video is about Newton's second law for rotation. And so I'm going to derive it in this video, and then we'll talk about a little bit what it means. And then in class you'll look at it in a lot of detail and do some problems. So I've drawn a circle, roughly, and there's the center of the circle. And I'm going to draw an object that is at the outside of the circle. And so that object is going to be at rest at this point in time, and we're going to say that because it's at rest, the net force on that object, whatever it is 0. And then I start to push on it. But before I push on it, I tether it to the beginning or the center of the circle. And so the object is now tethered to the center of the circle by some cable that has a length equal to r. And I'm going to start to push on that object. And I push with a tangential force. So I'm going to label it T just so we know it's tangential. It's not tension, so why don't I just say tangential? And so it's tangent to the circle, which means that this is a 90-degree angle that I definitely didn't draw accurately, but that's okay, you get the point. If I start to push on it, then the object is going to travel along the arc of the circle, because it's, again, tethered, and so as soon as I push, there starts to be tension in this cable, and so that tension is going to pull on the object and keep it moving in the circle. If I just stand behind it and keep pushing, I'll end up pushing it around in a circle. Now, because I push on it, it's going to accelerate. So I introduce a force, and because it's the only new force on this object, it was at rest, all the forces were balanced, then I start pushing on it. This force is the same thing as the net force, and so it causes an acceleration that is proportional to the mass of the object. And so Newton's second law shows up immediately, because a net force is going to cause an object to accelerate. Now, I'm going to just manipulate this equation a little bit. The first manipulation I'm going to make is to say that because this is a 90-degree angle, the torque that this force exerts is just equal to r times F. And so to make this Newton's second law equation into second law for rotation, I want to translate force into torque. So I'm going to take this equation and multiply both sides by that value of r. And so I get force times that value of r, and that's equal to torque. So the torque that I exert is equal to mass times acceleration times whatever that r is. So, okay, great. Now it's an equation about torque, and it's kind of similar. I have that mass times acceleration times that radius. The second thing I'm also going to remember is that the linear acceleration of this object is equal to r times alpha. So, because it's moving around in a circle, it also has an angular acceleration. So why don't I get that in there? So that means that alpha is equal, so A is equal to r times alpha. So when I get that in there, I have torque equals mass times r alpha times r. And that's kind of a big mess, so let me just simplify it. I get this equation, torque equals mr squared times alpha. Now I'm going to put mr squared in parentheses for just a second. And what this essentially shows, if I go all the way back to the beginning, is that I had a force that caused linear acceleration. And that is true. If I start to push on this box, it's going to start to accelerate tangentially, but it's linear around the circle. That, by nature of the definition of torque, also produces a torque. So if I know that distance, I can multiply that force times r and get the torque. And if I do the same thing to the other side, I get what that torque does. And so the net force causes an acceleration. The torque causes an angular acceleration. It's a particle moving around in a circle, but it still counts as rotation. So we get this idea that for Newton's second law, we can say like net force causes linear acceleration, And also, now, net torque causes angular acceleration. So again, it's the same idea. Everything we've studied so far, and it will continue in rotation, is just an analog for what we already know in the world of linear motion. So the greater the net torque, the greater the acceleration. And then there's the question of, like, what the heck is mr squared? So if you go back to this and you say, okay, net force causes acceleration. That acceleration is inversely proportional to the mass. The mass, our word that was a placeholder for mass for at least a little while, was inertia. So acceleration is helped along by the presence of a force, but it is opposed by the inertia of the object. Well, with an object that's going to rotate, the inertia is a little bit more complicated. And in the case of this equation, it's equal to not just m, but mr squared. This is called the moment of inertia, or the rotational inertia. And it's only valid, this is for of a single particle. And you'll see why in a minute. Okay, so that moment of inertia for a single particle, we give that the equation I equals mr squared. So, like, how does this show up in, like, what we're doing in physics? First of all, kilogram meter squared would be the units. Kilogram meter squared. So I want you to imagine something. You have control over your own running pace. And you can also run in a circle. And it costs a lot of muscle strain to run in smaller and smaller circles because you're changing direction a whole lot faster. But what I want you to think about is, if you push off from starting blocks in like a 100-meter dash, you are providing as much force as possible and you're causing a linear acceleration. If you run around a track that's a circle, then you're doing the same thing. You're pushing off, but you're pushing off at a different angle. You're kind of pushing off into the circle a little bit, and to cause yourself to move faster and faster as you go around. For those of you who have done track or who are familiar with running around a track, you know that there are starting locations around the curved end of the track that are staggered, right? So the inside lane starts here, and then lane 2 starts here, lane 3 starts here, 4, 5, and 6. The person on the outside lane actually starts like way far ahead of the person in lane 1. And so that's a situation where when you start running, you are giving yourself an angular acceleration right from the beginning. The person who starts back here in the inside lane doesn't have to run it starts way back there because they actually have a shorter path around this arc. So lane 1 might look like it might start here, and the person running lane 1 would run that path. The person in lane 5, on the other hand, is running that path. And so this idea of moment of inertia is this person on the inside, if both of these people like push off with the same force and get the same linear acceleration, then this person's going to get here faster. They're going to have a greater angular acceleration because their value of r is smaller. They literally have a smaller distance to travel. This person, if they actually started at the same spot, and if the person in the outside lane was going to beat the person in the inside lane to this finish line, they would have to have a much greater linear acceleration. So the inertia of an object that's going to move in a circle depends not only on the mass of that object, but also the distance it is from the axis. This is a literal further distance, and so to get to here in the same amount of time requires a much greater force to get there. And so this mr squared incorporates the ways that inertia shows up in rotation. Now, as soon as we teach you about this, I want you to forget about this equation pretty much in its entirety. You might use it a couple times, but it is not the focus of this course. Okay, so if we take this variable I, we get this equation, torque equals I alpha. And it's supposed to mimic, F equals ma, where everything is analogous, right? So force becomes torque, mass becomes moment of inertia, acceleration becomes angular acceleration. Now, this is just one particle. And so what you want to understand is in a big extended object, like the meter stick I keep using in class, if this line, instead of being a rope connected to the object, is actually just a meter stick, then every particle of that meter stick will be accelerating. If I exert a torque anywhere, maybe on the end of the meter stick, it's going to cause the entire meter stick to rotate. What ends up happening is for a full extended object, extended objects are like objects that we don't do free body diagrams as like points. So if we have a meter stick, that's an extended object, each particle of that meter stick has its own value of moment of inertia and experiences its own value of torque, even though the entire object has the same angular acceleration. So this is important to understand, even if we never use it, that these angular values are always the same for all parts of an object, even if the torque and I values are different for each particle. And so the way we get to the true Newton's second law of rotation is to say, well, if we do torque equals I alpha for every particle of an object, then all we're doing is we are adding all of the torques together. We are adding all of the moments of inertia together, and that is coming along with an angular acceleration. And so when we write Newton's second law for rotation, we do net torque equals I alpha, because the true way that we do moment of inertia is that it represents the sum of mr squared for each object. Now, I will give an example of this in class, because I'm running out of time for this video, but I'll give an example in the class of like how you would use this equation. But these two equations are very much not important in this course, and you'll see why when we start to do some problems. But this, Newton's second law for rotation, your net torque equals I alpha, is the kind of governing principle around rotation, and so that's what we're going to use in some practice problems.